me perform a sound check, but we are now in our recorded lesson. I'm going to be talking about, let me see if I can show time, view, yep, okay. All right, so we are starting our class today. And what we're going to do is we're going to go through the basics. So there's a few reasons why I'm doing this as I am. I really want to show where we are in terms of time. That'll keep me on track. All right. Well, I don't have the option right now, but so welcome to the course. It's going to be PW231, and it's going to be taught separately. So let me just go through some basics for you, and I'll write it on a whiteboard. Now, the theory part is going to be online and asynchronous. So I'll be recording these sessions and posting them for you. Now, I'll be doing live recordings on what I'm hoping is going to be, so this is PW231. So I'm going to be doing the recordings on Mondays. So this is week one. Let me actually switch my camera so you can see what I'm writing. We're in week number one. See if I can make this look a little bit better for you guys. And the lab is going to be taught by Professor Jovan. Oops, I lost my video here. I can get that back. Not really sure why I'm having so much trouble. Okay. So yeah, so the lab is going to be taught by Professor Jovan on campus, while the theory, that's me, going to be Professor Sajjad, and it's going to be asynchronous, and it's going to be online. Now, the only one caveat to that is I might ask you guys to meet me at a certain time for the tests. Now, the time I haven't determined exactly when, but it'll be Monday afternoons when I do the live recording, or afternoon or evening, likely evening, live recording. And it's going to be about an hour and a half to 2 hours. Now, if people are attending, I'll leave some time for question answers. But in terms of the actual content, because we had a week where we don't have a Monday, so that's why I'm doing this recording now. Okay, so that's why I have this recording up as it is. So let us now proceed. Let me change camera. Now let's go through some of the content. So the materials that you're looking for can be found in the course shell. As you can see here, course shell has the material. And all you have to do is focus on week one theory when you're working on my stuff. So today we're going to have a basic lecture. We're going to start with the lecture. And then we're going to go into, well, first we'll talk about the course outline, and then we'll go through the basic lecture with you guys here. Oh, there you go. I've got LinkedIn and Facebook open as well. Anyways, and I'll give you guys some homework. So we'll be about 45 minutes. here, and then we'll have our homework for you guys later on, where you can go through some of the stuff on your own and be ready for week number 2. All right, so let's now get into the course outline at this time. So if you look in the first week, you'll see we do have a course outline posted for you. So the course is PW231, and you have 2 hours per week for the theory and 2 hours per week for the lab portion. And that, like I said, will be handled by Professor Jovan. I'll be focused on the theory. So before we really get into the course content or go any further into the discussion on this week's topics, let's go through the acknowledgement of the traditional lands. So Centennial is proud to be a part of a rich history of education in this province and in this city. We acknowledge that we are on the treaty lands and the territory of the Mississaugas of the Credit First Nation and pay tribute to their legacy and the legacy of all First Peoples of Canada as we strengthen ties with the communities we serve and build the future through learning and through our graduates. Today, the traditional meeting place of Toronto is still home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work in the communities that have grown in the treaty lands of the Mississaugas. We acknowledge that we are all treaty people and accept our responsibility to honor all relations. So we're basically going to look at groundwater and soil in this course. So you're going to be doing some lab experiments as well. In my portion, we'll be looking mostly at the theory. So what are the successful learning outcomes that we're hoping to achieve? You should be able to understand what are the different main soil types by the end of the course. What are the different physical processes that are involved with the soil? And to test the soil for water content, density, etc. So that's what you'll be doing in the lab. And you'll be able to understand how to do soil extraction and how to ensure the integrity of the sample as well. You should be able to perform calculations and tests for field percolation, plastic limit, liquid limit, etc. by the end of this course, and you should be able to calculate groundwater flow through previous strata by applying Darcy's law. And you should be able to relate concepts like seepage velocity, coefficient of permeability, hydraulic gradient, and so on to aquifer flow. You should be able to also interpret plans from engineering reports and uh, analyze data and develop the right conclusions based on the soil characteristics. You should also be able to conduct lab experiments in a proper scientific format and distinguish between water, various clay minerals, and the interaction between water and sand. The essential employability skills are generic. You can go through them. There is no global citizenship. Again, there's 2 modes of presentation here or learning for you guys, teaching and learning. Number 1, it's online, which is this class. And I'll be doing the live recording on Mondays. I think it's going to be in the evenings. I'll mention it to you guys, and I'll also even share the link. So it'll usually be in the Teams within the course show, and I'll be recording it, and that recording will be shared with you immediately afterwards, just like this recording is. Now, the other item is uh, there are some textbooks, but most of what you need, I will be providing you guys. But if you want, these are the textbooks that you can get. And this is going to be made available to you as well for you, especially when you're going to be working on your operator test, your ELC test. Okay. And these are the items that we will bring to you guys. Now, I still haven't found the supplementary lecture notes. I'm gonna ask Professor Jovan if he can find them for me. because I don't remember seeing them. He's been helping me put this course together because he's been teaching it for years. So let me make a note here to try to get you guys the supplementary lecture notes. I can't find them. I'm sure he can help me find them. Okay, so here's the evaluation scheme, and I'm going to mostly focus on the tests. I do need a couple of assignments as well. So there's 2 tests and 2 assignments that I'll be taking care of. So that's 65% of the course will be in my class. And you guys all know the policy, but if you don't, make sure you understand it, that you do need to contact me immediately in order to get an accommodation if you do miss a test for any legitimate reason. And if you have an accommodation, please let me know. All right. Please remember this. You need a C in this and the other courses to go into third year. So please make sure you stay on track. All right. And if you want, you can take a look at the academic honesty policy. And here's the lecture schedule. We'll we will try to follow it as well as we can, but it's not going to be always possible. Sometimes there will be some variances where we do a little bit more or less, but we'll see how the course goes. I do I do want to emphasize that my goal is to make you as comfortable with the material as possible by the end. Okay. And there's a few things that I want to tell you guys about this course. Like, number one, I'm going to use the other pad for this. The 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 the, the work you're going to do here is going to help you if you get into the field of consulting, or if you are in conservation, or if you want to get into remediation, if you want to become a water technician. I would say this is helpful even if you want to get into the MECP or in a municipality. So this course is heavily uh, conducive to your future. Okay. Another thing I wanted to mention here is my background. So I am a professional geologist licensed in the United States, and I am also a professional geoscientist, licensed in Canada. And what that means is that if you go to a court of law and they want an expert opinion on something, they would hire somebody with these type of designations. Also, a lot of the reports, not all, but a lot of the reports need to be signed and sealed by somebody who holds these designations, or it could be a professional engineer. I also, till recently, was also a CET, which is something I encourage you guys to get. The reason why I stopped getting it is because I just didn't really help me as it being a PGO. So this is also known as a PGO, and this is known as a PG. It didn't really help me because I didn't really need to work on it. I didn't need it for my work. I did have it, but then they started to really increase the fees, which made it cost prohibitive for me, and the college stopped covering it as well. Now, my first experience working with groundwater was, or at soil and groundwater was 1995 when I started working on my research project where I did a groundwater modeling project. So it was a series of calculations that was run by a computer. And since then, so what is it now? 2025. I have worked as a field geologist, a hydrogeologist, A geophysicist is a geoscientist, basically focused more on soil and groundwater. So that is why I am in this area teaching you guys about these topics. Hopefully I can do a decent job, because if not, you will struggle with these concepts later on. You'll need these concepts later on in the course, in the program as well, especially if you go into third year, where we do spend a lot of time talking about soil, groundwater, flow maps, flow nets, and so on. All right. We'll give you guys a few moments to see if you have any example. Any questions for me? Oh, I forgot. We don't actually have a live recording, so I guess I could continue. So we covered. So let's get into the lecture slides. Okay. So what I'd like to do is, at this stage, is I'd like to go over a bit of history as briefly as I can, but it's important to go over, in my opinion. When we study geoscience, when we study geoscience, what are we looking at? As an environmental professional. So let's just try to draw out some of these. So you've got the surface of the earth, where we are. You've got your buildings, and you've got your soil. So it could be one of two. It could be fill or native. And it's basically one of the two. And it can also be called overburden. And then you have your, I'm gonna make it like this. You have your shallow or weathered bedrock. You have your shallow or weathered bedrock. Let's get a different color for the next layer. And then you have your consolidated bedrock. Consolidated. Consolidated bedrock. Hopefully I spelled that right. And then way below that, you may have your basement rock. Way below that. It's usually igneous or so on. So you've got your basement rock beneath that. And it's usually here in the overburden that you have your groundwater. And we can depict it with an inverse triangle. So this all exists within the crust of the earth. This all exists within the crust of the earth. And that's usually, the bedrock, or the consolidated bedrock is as deep as we usually go. So you've got your crust, and that's what we generally deal with. And then you got your mantle, as in fact, if you look at the and then way down, you have your core. You have your outer core and inner core. These are the different layers of the Earth. These are the different layers of the Earth. But how did we get to this point? Like, for example, why do we have silicates here, where we have more heavy metals down here? How did we get to this? And how did the Earth get to this stage? What happened in the past? So for that, we have to look back into the past billions of years. So after the first Big Bang, or well, there's not first the Big Bang, there's no first. You had hydrogen forming, and then this was then it started to fuse at the center of what became stars to form helium. So then fusion started to occur because gravity brought the materials together. Stars were born. This is in stars. And nuclear fusion continuing until these first generations of stars became so big, so dense, that they underwent a supernova. They underwent a supernova. And the material spread out, and some of it started to come together in the form of a gas nebula. So that's a supernova explosion. But remember, it's still billions of years ago. And that gas nebula might have started to form a star at the center and then planets around it under gravity. And then a new star or new star system, Sol, which is our star, that's the name of the sun, was born. And that's how the 8 planets formed. And it was basically under accretion as materials came together, right? So let's now watch somebody tell us about this in a little better manner. Give me a second here. Take a look at this. Share this with you guys. Share sound, optimize video. Hopefully you guys can hear this.
I see results with Tai Chi.
Day 3, you'll feel your energy. Day 7, your eyes will change. Day 28, you will become
This is the story of our Earth's formation 4.5 billion years ago, and of a little asteroid called Bennu, who's also survived until now. We have the team at NASA to thank for bringing us this video.
The Milky Way, home to billions of stars, rising and setting over billions of worlds, including our own. In this vast expanse, how did our sun, the Earth, and the planets come to be? In recent decades, our understanding of the solar system's evolution has greatly improved, but deep questions remain. To answer those questions, astronomers are preparing to visit someplace very small. Asteroid Bennu. A lump of rock and organic material, the early building blocks of the solar system, of Earth, of us. Bennu is a time capsule, and its journey takes us way, way back, 4.5 billion years. The raw ingredients of Bennu and our solar system originated in a stellar nursery a vast cloud of hydrogen, helium, and dust. Our own sun doesn't yet exist. Nearby are hot stars like this one, quickly burning up its fuel and destroying itself in a colossal explosion called a supernova. The explosion destabilizes our cloud, causing it to collapse. In the geologic blink of an eye, 100,000 years, gravity and angular momentum flatten the cloud into a swirling disk. In the center, where molecules crash together tightest, a protostar revs up to incredible pressures and temperatures. Deep within the disk, clumps of dust not much larger than a grain of wheat are flash heated into droplets of molten rock, called chondrules. The source of this heat remains a mystery. Chondrules are destined to become the building blocks of the solar system. Coaxed by gravity and turbulence, the chondrules clump. They grow into the first asteroids, into mountains, into planets. The asteroids are rubble piles of rock, metal, ice, and organics. This large asteroid is the parent body of Bennu, a protoplanet whose size we can only guess. Closer to the protostar, a planet begins to form. And then, dawn in the solar system. The protostar undergoes fusion and ignites, revealing our sun. But the solar system is far from finished. Jupiter most likely forms near its outer edge, but just 500 million years after the sun ignites, some believe that it slowly moves inward. Its massive gravity ripples the asteroid belt, disrupting countless asteroids and comets, flinging them toward the sun. They rain down on the inner planets, hammering and remelting large portions of their crust. Did these impacts also deliver organics and water, key ingredients for life? Back in the asteroid belt, Bennu's parent body is lucky. It survives this period of heavy
idea of how this started. Now I'd like to show you how the Earth was, because it's really astounding. It's basically accretion of material coming together. How the Earth was formed. It's basically material that was pulled together by gravity. Let's see, show you this.
Repeatedly misaligned during
So watch as the materials are starting to come together under gravity, and it starts to become larger and larger and larger. That's what the Earth looked like when it was born. This is the birth of our planet. And it's going to start to grow and grow and grow until you have larger and larger body, and the gravity starts attracting more and more material. It's like a snowball effect. And that's just a huge ball. stage, it's still very, very molten. It's still attracting materials. This is what I believe the early moon looked like. And it actually, the early moon, you can have a collision with the why do you see all these starts to look more and more like the early Earth. You can see there's an atmosphere now. And that protects us. A lot of stuff burns up before it gets to the surface. Okay, so that was the early,
Hey, I'm saving.
early Earth. We're probably gonna watch something. I'm gonna give you guys homework to watch. So let's get into the slides as we come near to the end of our first session. So I'm going to continue to give credit to Professor Jovan with the materials that he's provided for this. Thank you for that. So, source of soils. So now we talked about how the materials came together, but what happened is that over time it settled into different layers. You've got your crust, you've got your mesosphere in the mantle, and then you've got your outer core and inner core. So the outer core is liquid and fluid. The inner core is solid. Now, when we talk about the crust, we should include the, the lithosphere, but also has water in it. So the hydrosphere. Remember, there's 4 spheres that we are dealing with when we look at things from an environmental point of view. The geosphere, that's the solid material. The hydrosphere, that's the liquid. The atmosphere, that's the gaseous material. The atmosphere, like oxygen, nitrogen, and so on. And lastly, you've got the biosphere. That's us, that's life. Our main intent when we are working as an environmental professional is what? To protect the environment? Yes. But what we want to do is we want to protect us, the biosphere. But yet, this is how the Earth is split up. And if you want to look at it a little bit more closely, you've got the atmosphere here, got the hydrosphere, got the oceanic crust, and then the continental crust, which is much thicker. You've got the lithosphere, the mantle, and we know that the lithosphere is the asthenosphere, which is a weaker solid. So the Earth's crust is basically composed of rock and soil. Now, soil is actually just broken down rock material. And it just if you want to look at it purely from a geoscience point of view, it's broken down rock material. As you can read here, it's particular matter. And if it wasn't for this broken down rock material, you wouldn't be able to do so much of what we've been able to do as a human civilization, like grow crops, use the soil for construction, have the soil become a part of our lives. And when we're working in this business, what we're looking at in the soil are the voids between the particle. Why? Because the voids are where you have air, soil vapors, and you have water. Another thing that's important is to understand something, that our planet is not stable, completely stable. What do I mean by that? What do I mean by that? It's always in some sort of flux or motion. Change my camera again. And this is what we refer to as plate tectonics. So when the outer core or inner core or the core was being formed, there's a fluidity to it. And what keeps driving that fluidity? Heat. Now, yes, we had collisions and we had an initial heat that was caused by during the formation of the Earth. But why is it still so hot? So two things. Radioactive decay from unstable nuclei help keep the heat there, and friction. This is also why we have a magnetic field. But what this does is it keeps everything in motion. So our entire planet, the surface, the crust, you've got plates that are in motion. You know, this doesn't really write. I'm gonna have to throw that away. We have plates in motion. We also refer to this as plate. Shoot, this is not very good. Plate tectonics. Because the heat of the inner Earth causes the plates to be in motion. The crust is broken up into plates and it's in motion. We don't feel it because it can be quite slow, but it's the pressure that builds up between the plates that causes earthquakes. And if you look at the plates now, compared to what the plates looked like 250 million years ago, it's vastly different. This is what the plates look like now. We've got the North American plate, Caribbean plate, South American plate. You've got the Juan de Fuca plate, the Pacific plate, and so on. Now, one of the more interesting plates is the Indian plate, which is pushing upwards into the Eurasian plate, and that's why you've got the mountains. This is also how mountains are formed. As you can see here, you've got continent versus continental collision, and you've got crustal uplift, which causes the creation of the mountains. And then these mountains are then eroded over time. And that's how soil forms. Soil forms from weathering and erosion. So I'm going to leave the slides for now. But what I'm going to do is I'm going to ask you guys to do a few things. I'd like you guys to spend some time going over the slides that I've posted. And I'm going to try to find that book for you guys to help you guys make it a productive first week. I know this was not ideal. So what you want to do is go through the slides for your homework. Go through slides. Take a look at at least up to what we talked about today, at least up to today's topics. Okay. And I'll see if I can find you that companion book. That should make it easier for you. Okay, and then take a look at that. Go through the course outline again. And lastly, watch the clips that I've posted. Which clips are those? Let's take a look. So these are the clips that I'm referring to. The Earth's evolution in 10 minutes, Bill Nye's The Rock Cycle, because what we're talking about right now is the rock cycle and the graveyard at the center of the Earth. So watch
Earth's
these.
mantle. And those features are pretty good evidence that
Watch these.
Been pummeled by asteroids,
Help you guys
crashed
understand-
into other planets.
Understand our Earth a little bit better, okay?
Rocks! Did you ever stop to think that the
And
whole
that-
world is covered?
That is all I have for you guys for this week. So it's a more of a relaxing start. But just a reminder that we will have our live recording Mondays. So you can attend. If not, I will post the recording because it is asynchronous. But then it's up to you to make sure that you watch it. All right. Okay, so that's all I have for today. If you have questions, please do email me. Email me and we will try to sort it out. All right. We will try to help you guys understand whatever you need understanding with. Oops, my camera's going to give you a headache now. Sorry about that. Okay, and I'm hopeful that we were able to cover off enough things to help you guys get started. If not, again, we can go through stuff again next week. And I think you're going to have the start to your lab sessions this week as well. All right, so have a good rest of the week. And I'll see you in class or in a recording session.